So again, here is the general thing that is meant when we say system of differential equations. It could have more than just two, but I'm just going to write things assuming everything is two-dimensional. So you've got x, y, and possibly z, w, etc. X prime, y prime are given by these two functions that each of which could involve x and y and t. But this is too general to really study as it stands for us. We are going to focus on linear systems of differential equations with constant coefficients. So not just systems of differential equations, but linear with constant coefficients. And in fact, we're going to make it even more specific. But first, what do I mean by linear with constant coefficients? I mean something like this. So instead of x prime equals any old function of x, y, and t, so possibly something super complicated like sine x, y over t, or something stupid like that. Instead, something a little bit less complicated. Ax plus b, y, where a and b are constants, these are the constant coefficients, plus and then any old function of t. So this function of t could be very complicated, but it can only involve t. And then the way in which the right-hand side here depends on x and y is very simple. It's this linear type thing. And same for this one. But you could have different coefficients here and here, and different functions of t here and here. So that's what is meant by linear system of differential equations with constant coefficients. But what's linear about it? So let's see. Let's try our best to package things together here. So let me first erase these equal signs and then write just one equal sign and then consider it to be an equality between two sort of vector quantities. Now anytime I see a sum, I can think of that as vector addition, right? So I can make this plus sign actually be one plus sign between these two vectors. Let me give these some space here. So this is the same system of differential equations, just things are packaged together a little differently. Now look at this portion. We've got the same x and y showing up, but two different linear combinations. The first row is like ax plus by, and the second row is like cx plus dy. This reminds us a lot about what happens when you apply a 2x2 matrix to a vector. So this is like applying the matrix ABCD, that 2x2 matrix, to the vector xy. So let me write it that way. It's ABCD applied to x, y. Right? If you do this, then the first line of this, this is matrix applied to vector, and you get a vector, right? And then the first line of that vector, the first row will be ax plus by, and the second row will be cx plus dy. So this is exactly the same thing there. Now, let me make this look even more compact in notation by calling this matrix capital A. So let's call this matrix, let me write it separately over here. Capital A is going to be the matrix of constant coefficients, A, B, C, D. So the constant coefficients are now inside this matrix. And let me just call it capital A. Do you see any other ways to make this more compact? We can use our notation where we say vector x is our way of packaging together x of t and y of t into one vector. So this is now vector x of t, right? And then over here on the left, this is x prime, vector x prime, right? And can we package this together? Yeah, as long as we write down here what we mean when we write vector f of t. Let's use that to denote f1, f2. Then let me replace this by vector f of t. And look at that. That's so nice and compact compared to what I had to start with, right? You just have to know that all these things are defined in these different ways. But instead of saying all this junk, you could just say, you know, f is any vector-valued function, and A is just some 2x2 matrix of constants, constant coefficients, and x is our unknown function, which is actually two functions. So it's our unknown vector valued function. The beauty of writing things in this kind of format is that now you can go from two-dimensional systems to higher dimensional systems for free. So the three-dimensional version of a linear system of differential equations with constant coefficients is just going to have f1, f2, f3, three of these functions here of time. A will be a 3 by 3 matrix, and x of t will be like x of t, y of t, z of t. So, and all that comes at no cost to the notation. You write the same thing here. So that's really quite nice. Now the real reason I'm doing this is so I can quickly manipulate. So I'm going to move this part to the left-hand side. Not much is changing, right? But now it's starting to look like a more familiar sort of thing, right? It looks a lot like those things that we refer to as linear first-order differential equations, right? I think we previously wrote those as x prime plus p of t x equals q of t, something like that. And yeah, this is back when we talked about the method of integrating factors for solving this, if that helps jog your memory. This is what we called a linear first-order differential equation. See, this is looking like the same thing, right? Except the q of t is now this vector function. The p of t is now this matrix, and it does not depend on time, but you could imagine having non-constant coefficients, right? And having these matrix entries depend on time, and having this be a of t, just like you had the p of t before. We could totally look at that at some point, if we wanted to. And yeah, sure, here there was a plus and here there's a minus, but big whoop, who cares about that? So it's really starting to look like what we previously called linear first-order differential equations. And it really is linear in the following sense. If you look at what's happening to the vector of unknown functions x on the left-hand side, it's d dt, that's what's happening here, minus the matrix A applied to x, right? This is what you're seeing on the left-hand side here. You're seeing d dt, so this derivative operation being applied to x, minus A being applied to x. So this, you could call this L, right? And so suddenly, the kind of differential equation we're looking at is still one of this form. It's just that the vector, so x of t, it's just that the function that's going in is now a vector of functions, and the function that you get coming out is a vector of functions. So you see how we got here from this? You see how we got there from this? This we call a linear first-order system of differential equations because you can write it like this, where L here is this, which is a linear operator. So this, if you want to, you can check that this ends up being linear. So that's why these are called linear. And there's actually another adjective you can put on here, homogeneous or not homogeneous. So what do you think of this? Is it homogeneous or not homogeneous? Or what do you think when I write it in this format? Homogeneous or not? Probably almost everyone is thinking no, but some of you, I bet, are thinking no for the right reason, and some are thinking no for the wrong reason. This is not homogeneous, but the problem is not this. That's fine. It's the presence of these that make it possibly not homogeneous. If these are not zero, then it's not homogeneous. What you need to do is move the x stuff to the other side, then write it like this, kind of, and then look, is this zero or not? When this right-hand side is zero here, when these parts that contain explicit time dependence here, when these are zero, then you say it's homogeneous. And here, what I'm describing, since I've written f of t and I'm not assuming it's zero, I would say what I'm showing here is non-homogeneous. So there are several very nice advantages of writing things in these compact vector matrix kind of notations. So I've already mentioned that you can go up from 2 dimensions to higher dimensions without any notational cost, right? Just declare that this is now a 3 by 3 matrix, and these are vectors with 3 rather than 2 entries. There you go, three-dimensional system. But also, now all the tools of linear algebra become available to us. The things that we have observed previously about linear systems still apply when you look at things this way. So, for example, how do you approach this non-homogeneous linear system? Previously, we had a very general theory where the way I described it was we had these 3 steps. First, get a general solution to the homogeneous linear system, then somehow get some particular solution, some solution to the non-homogeneous version, then add them to get a solution to the full non-homogeneous linear system. All that still applies here. That's still what we're going to do, because we still have linear operator applied to unknown vector, this time vector of functions rather than just one function, equals another vector. What we will focus on for the sort of beginning portion of chapter 4 is homogeneous. So how do we deal with the homogeneous version? And I actually don't remember at what point we get into non-homogeneous. We probably do at some point, maybe? I don't know, but for some reason I'm forgetting how the course ends. But for now, we're definitely focusing on homogeneous for a while. So I just lopped off these f1 of t, f2 of t, assume there's no time dependence, and we're just looking at this. So a compact way to write this is x prime equals a x. This is the nice compact way to write it, where what's meant by x is a vector of unknown functions x, y, and what's meant by a is a matrix of constants like a, b, c, d. So this is the kind of thing that we're going to focus on for a while. It looks very simple, but we'll see that when we unpack this, there's a lot of depth. There's a lot that can go on with this notationally simple looking condensed thing here. So that means we're looking at a homogeneous thing, because if you subtract the a over and write things like this, then the f part is 0, right? So we're looking at the homogeneous case to begin with.